Hi, everyone. Welcome back to section 1.4. At the end of 1.3, we very briefly talked about the fact that the discriminant can be negative in quadratic formula. Well, that's kind of an issue because the discriminant usually sits inside a square root. So we're saying that we can take square roots of negative numbers, which to this point, we have not been able to do. However, what we are going to introduce in this section is the complex numbers. So before I do that, I just want to very briefly discuss what the complex numbers are. All the way in P1, we talked about the natural numbers, which were the counting numbers 0, 1, 2, 3. And we said the natural numbers sit inside the whole numbers, and the whole numbers sat inside the integers. The integers sat inside the rational numbers. And then we had this weird little set on the outside, the irrational numbers, and both the rational and irrational numbers made up the real numbers. So the real numbers are any numbers that, even if not pretty, even if not easily calculable, do sit on the real number line. For example, you may not necessarily know where exactly, negative 1.12479 sits, but you have an idea and you can picture where it sits. However, what we're going to introduce today is the complex numbers. So the complex numbers are this set that includes all of the real numbers, and we denote it with a capital C. And what we're going to add in this set are what are called imaginary numbers, where we are now allowed to take square roots of negative numbers, even if we cannot necessarily visualize what the square root of a negative number is. It does have very many properties, both in this course and in all of mathematics and in the real world. So just wanted to give this brief visual, and now we're going to move back to the presentation. Okay, so now we're back in the presentation. Now you see the name of the section, the complex numbers. So let's get right into it. So like we said, the natural numbers go inside the whole numbers go inside the integers go inside the rational numbers. Along with the irrational numbers, the rational numbers go inside the real numbers. And now this real numbers set goes inside what we call C, the complex numbers. Now, the complex numbers introduce the unit I, where we say and where we define I to be square root of -1, but not specifically just square root of -1. We have the added property that I squared equals -1. So normally we have these rules that when we square a square root, we're supposed to get positive numbers and all that. But in the set of the complex numbers, this is a rule that is allowed to happen. So again, just because we have I equals square root of -1 doesn't necessarily mean that all of our numbers are going to have I, or are going to be imaginary. The real numbers sit inside the complex numbers. So just like all natural numbers are whole numbers, just like all whole numbers are integers, all real numbers are complex numbers. So even if it doesn't have an I, it is still a complex number. So we use the notation Z equals A plus BI. Z is what we use to denote complex numbers in general. Instead of a C, right, we like using C for constant. So Z will denote complex numbers. So we have A plus BI. That is what a complex number would look like. A and B themselves, ignoring I for a second, A and B are just both real numbers, numbers that we have dealt with before. We say A is the real part, and we say B, the part that is attached to the imaginary unit I, is the imaginary part. So the part that is attached to square root of -1 is the imaginary part. We can visualize the real part. This could be like 2, and you know where 2 sits, but you might not necessarily know where 2 plus 3i sits. We can also call it the complex part, imaginary part. We get the idea. Now, if A equals 0, well, then we have 0 plus BI, which is just BI, and a number that only has an imaginary part, we say is purely imaginary. And if B equals 0, so A plus 0i, well, 0 times anything is still 0, even in the complex numbers. And that would give us just A, which itself is a real number. So one kind of added property, but goes along with what we're talking about, that if we have some B that is positive, so square root of -B, where this isn't positive, this is a negative number. Okay, square root of negative b, we separate this by saying square root of negative 1 times square root of b, right? Breaking up the product. And then square root of negative 1 is just I. So we say this is I square root of b. Okay, now I want to stress that this breaks the rule of radicals that we talked about all the way in P6. In P6, we said we can only separate roots if the insides are both 0 or positive. But in the complex number system, we are allowed to separate them. That is a rule of the complex numbers. Now, that's kind of unfamiliar to many of you if you have not seen imaginary numbers before, but essentially there are more than just the real number system out there. The most common number system, the one that we're most familiar with, is the real numbers. All numbers that we can add, subtract, visualize, graph, stuff like that, but there do exist other number systems that have their own sets of rules. Complex numbers is the beginner of sets that break apart from the real numbers. But if you go higher up in math, you can find all sorts of very, very crazy number systems. So I just want to stress that the complex numbers are their own set, are their own system, just like the natural numbers, just like the whole numbers, and so on. Okay, so just to get an idea on what real parts and imaginary parts look like, 2 plus 5i, well, this is a plus bi. The real part is the part that sits by itself, and the imaginary part is the part that is attached to I. So the real part here would be 2, and the imaginary part would be 5. Okay, pretty straightforward. 7 minus 1/2 I. The real part is the part that doesn't have I, which is 7. The imaginary part isn't just 1/2, it would be negative 1/2. Okay, that makes sense, the negative sign. 3i, well, 3i is completely missing a real part, right? It only has the I part. Well, we can rewrite this as 0 plus 3i. Well, now it's a little clear that the real part is 0 and the imaginary part is 3. Negative 9, completely missing the I part, but we can rewrite negative 9 as negative 9 plus 0i. Okay, well, the real part is negative 9. The imaginary part is 0. So if the imaginary part is 0, we would say it's just a real number. Negative 9 is a real number. We know that. And for the case of 3i, where the real part is 0, we would say that's a purely imaginary number. 3 plus square root of negative 25. Well, we have to simplify square root of negative 25 first. In general, always simplify square roots of negative numbers before you do anything else. Well, the square root of negative 25 would be the square root of 1 times the square root of 25. Square root of negative 1 is I, and square root of 25 is 5. Another way you can look at this is the square root of positive 25 is 5. So the square root of negative 25 is 5i. And you can extend that to all square roots of negative numbers. Square root of 64 is 8. Square root of negative 64 would be 8i. The real part, now that we have it rewritten, is 3, and the imaginary part is 5. Okay. Now, what we're interested in doing, of course, is all sorts of operations. All these operations will eventually get us back to quadratic equations, just like we finished 1.3 with. Okay, so some operations, addition and subtraction, they are a lot like combining like terms for polynomials. So if we are adding or subtracting complex numbers, we are going to add and subtract their real parts, add and subtract their imaginary parts. So kind of thinking about this as combining like terms, you add all the constants together, you add all the x's together, all the x squareds, and so on. So 2 plus 3i plus 1 plus 4i, we are going to add 2 and 1, and then separately add 3i and 4i. Well, 2 plus 1 is 3, 3i plus 4i is 7i. If you want to substitute x in for I, just so it's a little bit easier to look at, that's totally fine too. 3 plus 7i plus 2 minus 4i, we're going to add the real parts, 3 and 2, and then add 7 and negative 4i, or just subtract 7i and 4i. 3 plus 2 is 5, 7i minus 4i is 3i. 5 plus 9i minus 6 minus 8i. Let's be a little careful. We're going to subtract the real parts. So 5 minus 6 and 9i minus negative 8i for the imaginary parts. 5 minus 6, negative 1. Negative negative is a plus, 17i. If we have square roots, like I said, simplify the square roots. First, square root of negative 9 would be square root of negative 1 times square root of 9. Square root of negative 4 would be square root of negative 1 times square root of 4. Okay, well, square root of 9 is 3. Square root of negative 9 is 3i. Square root of 4 is 2. Square root of negative 4 is 2i. And now, just subtracting real and imaginary parts. Okay, so not so bad so far. And multiplication isn't that much different, except think about this. If you have been thinking about I as x, well, when we are doing, for example, foiling and we get x squared, well, x squared just stays x squared. It's its own thing. But if you're doing it with I, we have the rule that I squared equals something specific. So it's just one extra step of simplification. So we say in the complex numbers that I squared is negative 1. So when doing multiplications with square roots, with imaginary parts, write the square roots as that I square root of b form before, and do that before multiplying. Okay, 3 minus 5i times 2 plus 7i. Let's treat this just like foiling. So we're going to do 3 times 2 is 6. 3 times 7i is 21i. Negative 5i times 2, negative 10i. Negative 5i times 7i, negative 35i squared. Let's simplify this inside right here. 21i minus 10i would be 11i. And now, if this was polynomials with x's, we would be done. However, in the complex numbers, when we're talking about I, we have one added step, that I squared equals negative 1. Okay, negative 35 times negative 1 is positive 35. So our extra steps just lead us to adding real parts. 6 plus 35 is 41. Now, we like writing 41 plus 11i. We like writing the I term second. That's just how we decide to write them. If you wrote 11i plus 41, you're not necessarily wrong. It's just a little bit nicer to put the imaginary part second. 2 plus 5i times 1 plus 4i. Okay, 2 times 1 is 2. 2 times 4i is 8i. 5i times 1 is 5i. 5i times 4i is 20i squared. 8i plus 5i is 13i. 20i squared, well, I squared is negative 1. So 20 times negative 1 is negative 20. 2 minus 20 is negative 18. So again, we kind of like writing that minus second, 13i minus 18. It is more correct to put the imaginary part second. So it's kind of interesting because all of these terms here are positive. And in polynomials, everything positive that we're multiplying, we end up with everything positive at the end. But we see in the complex numbers, we get this weird behavior that sometimes we can still get negative numbers. Negative 2i times 5 minus 9i. This is just distribution. Negative 2i times 5, negative 10i. Negative 2i times negative 9i, positive 18i squared. I squared is negative 1. So 18 times negative 1 is negative 18. Okay. 3i times 7 plus 4i. 3i times 7 is 21i. 3i times 4i squared, 12i. 3i times 4i is 12i squared. I squared is negative 1. So we get negative 12 plus 21i. So just be careful. Treat these problems as their own separate problems. In the event that you have square roots, simplify the square roots first. So square root of negative 2 is square root of negative 1 times square root of 2, essentially pulling out that negative 1 in terms of a square root. Square root of negative 8 is square root of negative 1 times square root of 8. Square root of negative 1 is I. Square root of negative 1 is also again I. So I times I is I squared. Inside the square roots, 2 times 8 is 16. Well, I squared is -1. Square root of 16 is 4. So our final answer is -4. And again, be very careful. This is true for the complex numbers. What we would do in the real numbers, but we wouldn't actually do it in the real numbers because we're not allowed to have square roots, negatives inside square roots to begin with in the real numbers. This is only allowed in the complex numbers. But just be careful. Make sure you simplify this with I first, because if you go right for combining the insides, you would get -2 times -8 is +16, and square root of +16 would be 4. So please be very careful. The rules of complex numbers dictate that we need to take out I first when we're dealing with square roots of negative numbers. Okay, and there's actually a really interesting property surrounding I and the powers of I. So we know that I to the 1 is just I. We know that I squared is -1. Well, then I cubed would be I squared times I, but I squared is -1. And -1 times I would be -I. Okay, but I to the 4th, well, I to the 4th is I squared times I squared. I squared is -1. I squared is also -1. And -1 times -1 is +1. Oh, that is weird. Okay. Well, I to the 5th would be I to the 4th times I, right? Just using properties of powers. I to the 4th is 1, and I is just I, so 1 times I is just I. Okay. I to the 6th, I to the 4th times I squared. I to the 4th is 1, and I squared is -1. Well, 1 times -1 is -1. I to the 7th is I to the 4th times I cubed. I to the 4th is 1, and I cubed is -I. So 1 times -I is just -I. Oh, well, hold on. I, -1, -I, 1. I, -1, -I. Maybe there's already a pattern. Okay, I to the 8th would be I to the 4th times I to the 4th, but I to the 4th is just 1, and 1 times 1 is 1. Look at that. The powers of I cycle. I, -1, I, 1. I, -1, I, 1. So what do you think is going to happen for I to the 9th? Well, I to the 8th was 1, so we cycle again back to I. I to the 10th would be the next one in the cycle, -1, and then -I, and then 1. I to the 13th, wow, look, the cycle is exactly the same. I, -1, I, and 1. Very, very strange. Okay, now, before we get into actually solving quadratic equations using complex numbers, we got to talk about division a little bit. And division is kind of weird. Okay, so complex division is a lot like rationalization. Go all the way back to P6 when we talked about rationalizing denominators, and that's going to be very, very, very similar to here. Okay, so what we're going to do is multiply by the conjugate. So the conjugate of A plus BI would be A minus BI, and vice versa. Think back to the conjugate of A plus B. Conjugate of A plus B is A minus B, and the conjugate of A minus B is A plus B. So phraseology is the same. Conjugate, its application is still the same, where if we have A plus BI, its conjugate is A minus BI. If we have A minus BI, its conjugate is A plus BI. So now the complex conjugate product theorem, very long mouthful, the complex conjugate product theorem says when we multiply these things, when we multiply something by its conjugate, well, A times A is A squared, BI times -BI is -B squared I squared. Notice we don't have to do the inside, that's just foiling. But this is also just difference of squares, right? A plus something, A minus something, difference of squares. Well, I squared is -1, so -B squared times -1 would be +B squared. Oh, that's really weird. Okay, so if we are multiplying something by its conjugate, if we're multiplying a complex number by its conjugate, all we need to do is take the real part and square it, and then add the imaginary part squared. Forget about the i's. No more i's here. So if you don't like what I just did, that's okay. You are more than welcome to FOIL, but this is going to save us a lot of time. So let's do z by z bar. That's what this little z with the bar on top, literally z bar. Okay, so if we're multiplying 2 plus 5i by its conjugate, we're multiplying by 2 minus 5i. Well, if you want to FOIL this, you can, but the complex conjugate product theorem says 2 times 2, take the real parts, square them, plus take the imaginary parts and square them. Take 2, square it, plus take 5 and square it. 2 squared is 4, 5 squared is 25, and you get 29. So again, if you want to FOIL, you can, but you don't have to. Okay. 7 minus 1/2 I, if we want to multiply by its conjugate, the conjugate of 7 minus 1/2 I would be 7 plus 1/2 I. And here is a great example of why you wouldn't want to expand this. Well, here what we're going to do is take the real parts, square them, plus take the imaginary parts and square them. 7 squared plus 1/2 squared. 7 squared is 49. 1/2 squared is 1/4. And properties of fractions, that's chapter P. 3i, well, 3i here is a little bit of a problem. There's no real part, but fear not. 3i is just 0 plus 3i. Okay, well, 0 plus 3i, its conjugate is 0 minus 3i. So take the real parts, square them, take the imaginary parts, and square them. 0 squared plus 3 squared. And we just get 9. Okay, now we did it this way so that it's a lot easier to do division. Okay, so what we're going to do for complex division is multiply by the conjugate, exactly like we rationalized the denominator. We don't want I in the denominator here. All of the complex numbers we've talked about so far have all been in the numerator. Okay, so the conjugate of 2 plus I would be 2 minus I. And just like everything else we've done, multiply it in the numerator and in the denominator. So what we get is 1 times 2i over 2 plus I times 2 minus I. Oh, look at this. Complex conjugate product theorem says take the real part 2, square it. Take the imaginary part, there's a 1 right here, and square it, add them together. 1 times 2 minus I is just 2 minus I. Real part squared plus imaginary part squared. 2 squared is 4. 1 squared is 1. 4 plus 1 is 5. Now, I like this answer. This is pretty clear. However, it is very mathematically sound to say 2/5 minus 1/5 I, just so it's a lot clearer that this is the real part and this is the imaginary part. So again, I would accept this, but those of you watching elsewhere, be careful. This might be better for your instructors. Okay. And again, if you don't like what I did, that's totally fine. You still have to multiply by 2 minus I over 2 minus I, but when it comes to the denominator, if you feel better foiling this, that's totally okay. 2 times 2 is 4. 2 times negative 2i is negative 2i. I times 2 is positive 2i. I times negative I is negative I squared. Well, we can simplify that inside. Negative 2i plus 2i goes away. I squared itself is negative 1. So 4 minus negative 1 would be 4 plus 1, and that's 5. And just like that, we get to the exact same answer. Okay, some more examples. 1 plus I over 1 minus I. We're going to multiply by the conjugate of the denominator, always. Conjugate of 1 minus I is 1 plus I. Okay, so in the numerator, we get 1 plus I times 1 plus I. We're going to need to FOIL that. But in the denominator, 1 plus I, 1 minus I, complex conjugate product theorem. Take the real part 1, square it. Take the imaginary part 1, square it, and add them together. Up here, 1 times 1 is 1. 1 times I is I times 1 is I, so we get 2 i's. I times I is I squared. Okay, well, 1 squared is 1. 1 squared is 1, so we get 2. And I squared is negative 1. 1 minus 1 goes away. So 1 plus I over 1 minus I is just I. Ooh. There is very little rhyme or reason. You should be trying to do all these problems on their own. Don't look for patterns like this. This is just a nice example that happened to work out. Okay, 7 plus 6i over 3 minus 4i multiplied by the conjugate of the denominator. The conjugate of 3 minus 4i is 3 plus 4i. In the numerator, FOIL this out. In the denominator, take the real parts, square them, plus take the imaginary parts and square them. So I FOILed at the top. At the bottom, 3 squared plus 4 squared. Okay, 28i plus 18i, 46i. 3 squared plus 4 squared is going to be 9 plus 16. I squared is negative 1. 24 times negative 1, negative 24. Alrighty. Nobody said these were going to be pretty. But now we get the idea. Okay, now that we have learned to sort of work with I, what we can now do is actually solve quadratic equations where we get two complex solutions. Okay, so when the discriminant is less than 0, our final answer is a pair of complex roots. Don't forget from the discriminants part in the last section that if the discriminant is negative, what type of solutions we get is two complex solutions. So x squared plus 2x plus 2 equals 0. Okay, well, A is 1, B is 2, C is 2, just like we did in the last section. But now let's plug in all of that information to the quadratic formula. All right, well, 2 squared is 4. 4 times 1 times 2 is 8. 4 minus 8 is negative 4. Okay, well, the square root of positive 4 is 2, so the square root of negative 4 is 2i. And now we can divide everything by 2 to get negative 1 plus or minus I. Okay. X squared minus 4x plus 13 equals 0. A is 1. B is negative 4. C is 13, right? Just to reiterate, ax squared plus bx plus c. Alrighty, and just plug it into quadratic formula. Negative 4 squared is positive 16. Negative 4 times 13 is negative 52. 16 minus 52 is negative 36. Square root of positive 36 is 6. Square root of negative 36 is 6i. And we can divide both 4 and 6 by 2. Nice. One more. 4x squared plus 4x plus 5 equals 0. A is 4. B is 4. C is 5. Plug it all in. 4 squared is 16. 4 times 4 times 5 is 80. 16 minus 80 is negative 64. The square root of negative 64 will be 8i. We can divide all of these things by 4. And just like that, that's the end of 1.4. So most of the section, even though our goal was to solve quadratic equations that involved I, what we ended up doing is spending more time just doing complex number acrobatics. So yeah, that's the end of 1.4. And 1.5, we're going to extend what we did in 1.1 and 1.3 to solve equations that have almost any power and a whole bunch of other weird looking things. So I will see you in 1.45. in 1.5. Bye. Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.